Advisory Board, and I think that many of you probably don't know who we are. So if you're a member of the Alumni Advisory Board, could you raise a hand? Or yeah, so some of you can see. And so we're a group of people who were like you. We were students in this department at one point or another, and probably a longer period of time ago, some of us younger. And we're just really excited to be able to celebrate the success that this department set us up for, the successes. And we're dedicated to helping the department because the department actually asks us for advice from time to time. It's rather unusual. So we're really glad to be able to give that. And one of the things that we do as an advisory board is we celebrate other alumni. And so several years ago, we set up a Distinguished Alumni or Alumnus Award, which is given annually to a member, an individual who graduated from this program at some point, whether they got a bachelor's, a master's, or a PhD, and have gone on to do really great things. So this year, our awardee is Dr. Bruce Railsback. And I'm going to go ahead and open this. It's tough to open. So the award, before I introduce the speaker, is crafted on a piece of a windowsill from the building. Pardon? It's a stylolytic limestone, and it's a beautiful stylolytic limestone. And it's crafted by our very own Matt Wortell, who was an undergraduate when I was a doctoral student here. And it is also always awesome to come back and see Matt. Matt does a beautiful job, and he really went a step beyond this year and included some gold. It looks like gold flake there.
Gilding.
Gilding. Thank you. And I'm told that it's sealed so that you can rub your finger across it or however you wish. It's not lick it if you need to. You know, we are geologists. We're going to do the Harvey Black method on this thing at some point. But Bruce, I want to present that to you and congratulate you. And we can let me introduce you if you want to stand up. So as the chair, I will congratulate you.
Thank you.
And yeah. So it's magnetic. Beautiful.
Shaking hands.
Oh. We're gonna have to do this. Look, we did it.
I think we did it.
Yes. So Dr. Railsback Bruce is three-time alumnus of this university. In 1980, graduated with a degree in history. If my notes are correct. Here we go. It's all written there. 1981, bachelor's in geology, and 1983, a master's in geology. And then he spent a brief period working in the prestigious sector of the oil patch that we call Shell, and went to the University of Illinois for a PhD, and has had quite a distinguished career as a research scientist, I believe all of which at the University of Georgia.
Yes.
Yeah. His research interests include the paleoclimatology and paleoenvironmental work, mostly through understanding carbonates, especially within speleothems, is my understanding. And among his many career awards and acknowledgments, he's a fellow of the Geological Society of America and has at least 90 peer-reviewed journal articles under his name and co-authorship. And today, without further ado, he's going to be describing to us and helping us understand better this earth scientist's periodic table of the elements in our eyes.
Thank you. Good afternoon, everyone. It is, of course, an honor to be here and accept this award. To me, it's an honor just to be at the front of this room because I sat up about there 40 years ago and had the privilege of listening to a lot of very dedicated educators train my cohort. And so I now look back and want to say thank you as I never did before. That began with Richard Baker teaching introductory geology and leading us on a spectacular field trip to Wisconsin that anybody who went on it, he of course scheduled it for a beautiful fall weekend. Anybody who went on it was hooked in terms of being a geologist. Took Keen Sweat's historical geology course, moved on then to George McCormick's mineralogy course, where he taught us a great course and scared us pretty well on the way. Then took petrology from the young Tom Foster, who by all logic, as a new assistant professor, untenured, ought to have been working like crazy to crank out publications, to get grants. Instead was spending his time generating lots of hand-drawn diagrams for that petrology class, and did a really spectacular job, like I say, especially given his situation. From there, went on to Bob Brenner's stratigraphy class, Gil Clapper's paleontology class, ultimately getting out of this room, because all those were here, upstairs to Dick Hoppin's structural geology classes. And so I had a great undergrad education. And then moved on to a graduate program here, where the outstanding course to me was taught by one Philip Henry Heckel, who had just a spectacular collection of samples in terms of hand samples, thin sections, all very carefully marked so that we would be looking at the right things in them. Every age of limestone, every depositional environment of marine limestone, and then in non-marine carbonates, lacustrine limestones, speleothems, tufas, travertines. I missed one there. Caliche. Just a spectacular class that he taught, and took us on a field trip to southeastern Kansas to see limestones there that got me hooked enough to do a master's thesis with him. But more, that was the whole foundation then of my career, as reported here, mostly thinking about carbonate things. And so it's looking back on what those people did as educators for students of the department then, that I come here today wanting to kind of pay back by doing mostly an educational mission here to talk about this thing called the Earth Scientist Periodic Table of the Elements and their ions. And in that spirit of coming here as an educator, I want to say, I certainly sent messages encouraging students to be here, and anyone else too. I want to encourage, ask me questions. Just stop me in the middle of this and say, well, what did you just say and why did you say it, if you need to. Because again, I'm here as an educator, not here as, I hope, a pontificator. So with that said, very reasonably you would say, well, what do we need another periodic table for? Because after all, we have kind of the classic periodic table, I think, as most people know it today. And if you don't like it, you can kind of push everything over to one side. Mostly I think about what the last orbital filled is. There are pyramid schemes. If that's not confusing to you, there's this, which spirals out, but nonetheless, I don't see how you can look at it, at least if you're of my age, and not see the floor plan of the Starship Enterprise. There are three-dimensional representations. And again, to stay on the same theme, brings to mind 3D chess, and we're back to Star Trek. Or actually someone has made something you can print out and make a literally three-dimensional periodic table. And if you spend the time, you can, in your mind, rotate that around. And yes, it is going to get you all the way around the table. So I think you can look at all those and say, well, why do you need a different periodic table? And my answer is, I don't think any of them are particularly good for the purposes of Earth scientists. And my first thought would be, all those periodic tables of the elements are doing what they claim to do, which to put the elements, or put what they're showing in places dictated by elemental uncharged form. But of course, if you think about taking basic mineralogy, that's not what we look at. we're thinking about things that have combined, and we usually think about that then in terms of charges attracting and so on. And so we, to take three basic mineralogy kinds of, in fact, probably just geology 101 kinds of minerals we look at, we're thinking about then the charges, at least as we reconstruct them on there. We are not thinking about elemental calcium or elemental fluorine. And in fact, neither one of them exist in nature. So that's not much good to a natural scientist. We're wanting to think about charged things, and the same with quartz and feldspars, et cetera, that we're thinking about charged entities. And so my thought would be, let's start a periodic table then where here we're thinking about stripping out off all the outer shell electrons, but putting charge on these things, and then saying, well, okay, that nonetheless looks kind of like the format of the periodic tables I was showing you earlier. But once we do that, we can bring over more things, and probably most importantly to a geologist, get silicon over here where we begin to talk about an awful lot of our silicate minerals, but bring those over, and then perhaps even more radically go down to the bottom of the periodic table as conventionally done, and drag up things that continue the sequence of +1, +2, +3, +4, +5, +6 charge, bring up thorium, bring up uranium, and I hope, if you are already with me on this, by the end of this lecture, to see these not as weird things down at the bottom of the table and what are they doing there, but to see them as part of a continuum where uranium down here, and I know in the back of the room this is hard to see, but uranium then part of a trend that starts all the way up here with phosphorus and chromium and things like that. And similarly, thorium, which previously was down there in the weird land, part of that continuum of red symbols there. We'll get to what those symbols mean, but the point is to begin to see trends across here that aren't evident to you in the conventional table. So that's my first thought about those previous tables. The second is because they were all done thinking about just purely something in its elemental form, they only had to appear once on the table. Why else? Why would you want to show them twice? But once you're saying you're going to think about charge on materials, lots of the elements take different forms and depending on what charge they're in. And so they're going to have to appear multiple times. And that's why this table begins to get kind of complicated, I admit, in terms of the number of things shown. No better example than sulfur. On the conventional periodic table, elemental sulfur's there, we're done. If we're going to think about what we see in nature, that would be what we call native sulfur, but we also know we've got all these sulfate minerals where our sulfur now has lost a bunch of electrons and has a +6 charge, all the way over to where instead it's gained a couple of electrons and has a -2 charge, and gives us minerals in kind of a weird way of combination of charge there. It gives us pyrite, a very common sulfide mineral. But we're really going to want a table that can speak to all these things. And so going to want to take where we were before and say, well, yeah, but I got to think about not only positively charged, but negatively charged carbon, where I was, not only intensely positively charged sulfur, but negatively charged sulfur. I'm needing to do that. And so on this whole horrendous table, go from negatively charged to positively charged sulfur, intermediate cases in between, uncharged in between. But if I'm really going to talk about everything we need to talk about, we need all that there. And sulfur's the one with the most possible different charges. So I'm taking either the best case or the worst case, I don't know which. But more than in here, say for example with molybdenum, need to think about where it's lost all its outer shell electrons and behaves in ways that have little to do with instead the ways it behaves where it's been ionized but has lost fewer electrons. So, like I say, for us to talk about all the things we need to talk about, we need all that. So, yeah, why yet another periodic table for those of us, and I would say lots of us in the more general earth sciences than just geologists, but the oceanographers, the ecologists, all that, because we work with a lot of different environments, and so elements appearing in different guises along the way. My third thought is the conventional periodic table. If you go to a chemistry class, You'll hear it talked about in terms of rows and columns. We're scientists. What are we going to do if we're given an array of data like that? We're going to contour it. It's what we start doing in Geology 101 is contouring topographic maps. And so on this left side of the table, where again, we're only looking at the elements as they have lost all their outer shell electrons, I've put on some contours here that I need to talk about. They are contours of what is called ionic potential, which is a very physicsy kind of expression. Potential in the sense that you think about voltages and concentration of charge, which isn't bad. Probably for us, easier to think about at the atomic scale in a crystal, density of charge, because you're going to take the charge of the ion, just divide by radius and get this term then we're going to call ionic potential. Calcium's really easy. It's always got a +2 charge. Our radius is essentially 1 angstrom. Even we earth scientists can divide by 1. So we can get 2 over here, 1 there, an ionic potential of 2, which thus far means nothing. But by comparison, and the math gets a little trickier, take nitrogen +5, the nitrogen in the middle of a nitrate radical, obviously a charge of 5. A radius is much smaller than up here because we have lost all the outer shell electrons. We're just left with basically a helium nucleus, or electron shell there. So a bigger charge, a much smaller radius, and get an ionic potential of 45, a much bigger number. The significance of that being now you're talking about, yes, a very itty-bitty little ion, but a tremendous beacon of charge. And that's why I've tried to make it red there, but even that doesn't do justice to the concentration of charge there. This is going to dictate how nitrogen in that oxidation, that very oxidized form, is going to then make minerals and behave in nature. To be clear, this isn't news. Many of you will recognize the name of Victor Goldschmidt. He publishing a paper here that basically the lines are representing different values of ionic potential. He actually has a list of things by ionic potential there. G.H. Cartledge, about the same time, making what begins to look kind of like a periodic table organized by charge on ions. So where I would be dragging you here. But I come back then to the array that I made, which you've seen so far. And for each thing, and again for calcium, easy, you get an ionic potential of 2.0. And like I say, being geologists then, we draw some contours through there. But my point would be, those then begin to define fields that match up with these, I know, as yet unexplained patches of color in here that begin to explain why matter is separating itself as we see it as earth scientists. That's where we're looking at atoms that have lost all their outer shell electrons, so-called hard in the sense of no fluffy electrons floating around out there in outer orbitals. The earth scientist periodic table then takes those contours over to here, where instead you're looking at the things that have some outer shell electrons. You're up to where, say, take iron. Its atomic number is 26. If it had all 26 electrons, it had 8 electrons beyond the argon outer shell configuration. It'd be a mess. But you can't get rid of all of them, so instead it's lost some of its outer shell electrons, but not all, to get it either +3 or +2 charges. That's what all this is about, is then thinking about those things that do have some outer shell electrons, but otherwise are the ions that we're going to make minerals with. For what it's worth, you can instead do that in terms of negative ionic potential over here. We'll get there, perhaps, before the time I have to shut up. But the point would be, yeah, we can transform that. And at this point, you're saying, yeah, and so you got your new table, but who cares? A very good question. I think the who cares question is that obviously I want to explain patterns of behavior of matter and nature. That's basically what at fundamental we're doing as our scientists. So now I come up here to where we have needed to be and say, what are all these funny looking red symbols about? And or I should have said funny looking just symbols, not the red ones I was thinking ahead. I'll start with the red ones. which are all about things that form solids at high temperatures. And so to take these first kind of through time, go back to the formation of the solar system. Solar nebula whooshing around here in almost entirely ionized material, but the first things to instead come together as solids are the things we call calcium aluminum rich inclusions, or everybody in the literature then calls them CAIs. But I'm going to stick a little starburst, thinking about the formation of a solar system, next to those then as we go to the table. So we're starting early there with the very beginning of a solar system, getting to the formation of the planet. My kind of supposed to look like an Earth there, and it's hot inside, so it's red. Is thinking about then the things that go into the mantle early in the formation of the planet and stay there. Don't get differentiated out to make the crust, but instead stay in that hot part. So again, the things that are getting in solids and staying there without being differentiated at planetary scale. And last, in time, because this could be magma being erupted this moment, mark with an I just for igneous, the ions that go into early forming phases at igneous rocks. So we're going to have to stick one of these on obviously magnesium +2 and iron +2 to make my olivine. Going to have to put one on calcium and one on aluminum to make my anorthite. So at the beginnings, the upper ends of Bowen's reaction series. Going to stick those symbols, these various red symbols, on things that are telling you about, hey, we readily go into solids and stay there. That's the red. It's the high temperature end of that thought. Kind of dulling down my red to brown is to take the same thought but at low temperature and say, well, okay, once you've made a solid, are there things that will stay in it? And so the things that are concentrated in the residual zones of soils, basically think of the B zone of soils, let's mark those with this, S for soil, and that's supposed to be part of a soil column. It's pretty bad art. But we're going to stick those there to say, yeah, low temperature. We're looking at the things that stay in solids by my solid lover, or where even aluminum will weather out a little bit and go into solution, little bit of aluminum and manganese, oxidized manganese, etc., in the ocean, but they settle, I shouldn't say settle out, precipitate out very quickly. Oops, sorry, I forgot, I don't even need to advance here. So my little FM brown round thing is supposed to be a manganese nodule, or a ferromanganese nodule, to say what in the ocean then forms, again, from things that really like to get into solids, in this case, at low temperature. So collectively, that up there is about those things that go into solids. Reds and browns, let's say the red, getting you to think about high temperature. By contrast, the greens and blues are essentially the opposite. The things that don't stay in solids very well, but instead get weathered out, either then are going to be abundant in groundwater or seawater. And so, start here, that's supposed to be a cross-section of a river channel. And so, because bicarbonate so dominates the chemistry of river water, it's the only thing that gets the big river symbol. But river water then with the next 7 most abundant solutes marked. So they're thinking about the weather process and the things that don't stay in solids, go into solution, take that river water to the ocean. And so you can see that as a beaker or a bathtub or whatever you like there. But the big symbol for the 8 most abundant solutes in seawater, and then smaller down to the 22nd most abundant. But again, thinking about the things that get out of solids into solution. And once you say that and think about, okay, what goes into solution readily, you then have, oh, sorry, I forgot, I had to get back up here to kind of the opposite of the ions that go into minerals, igneous minerals early. Here are the ones that go in late, and so are in the same category here of not really being happy in solids. Sorry, I forgot I had to go back and get that. Now I can say, thinking about things that are in solution, basically all your nutrients are going to fall in that category, because to get through the cell wall of an organism, even a single-celled one, they have to be in solution to do so. And so in the same sense that the blues, you're marking things that are in solution, the greens are technically telling you what are things that are nutrients in various various situations in the oceans, on land, etc. But the point is the same the same principle should hold in terms of there being soluble species. So with all that, you can come back and get this table. And let me say two things. This isn't made up. I did not say, well, you know, this goes into soils and that goes into soils, so I bet scandium does too. No, this represents, in some cases, very easy consultation of the literature, certainly to put the things that are most abundant in seawater. Well, you can easily get a table of that in about 5 minutes. Some of it involves going through the literature in great detail, because once you start trying to learn anything about scandium, you're going to have to dig a while, so to speak. So my point is, it isn't made up. Every one of those symbols is based on what's in the literature. And the second thought is, when I got to seeing that as it filled out, I was shocked how, to me, neat it is that you do have this track of the ions that go into solids, stay in solids, etc. That's what the red and browns are about. And on the other hand, these things that don't particularly, and instead go into solution, I had no idea this was going to work out as to me, cleanly and neatly as it does and become such a good, essentially predictive model. With that said, the next question might be, and why does it work out like that? And to do that, if you think that's a terrible diagram, this is probably worse. Although it actually, probably on this screen looks better, the type's bigger anyway. And again, it's kind of a periodic table. If you look, I'm going to go lithium, beryllium, boron, carbon, nitrogen. Down here, rubidium, strontium, yttrium, zirconium. It's a little warped to make the artwork behave. But what I want to do is talk about how solids either do or don't form. And I'll start over here. I'm just going to kind of work my way through, start one side or the other. Let's take, somewhere back there, I was concerned about nitrogen. Nitrogen plus 5, going to make a nitrate ion, bond 3 oxygens very tightly to it because you've got a lot of positive charge tightly focused there. So it's going to grab 3 negatively charged things and hold on very tightly to them. Another one here. So you get a nitrate group, like a carbonate group, stick on another white oxygen ball, a sulfate group, even a chromate group if you care. But you're looking at then that very tightly focused positive charge, holding on to those either 3 or 4 oxygens. But on the other hand, have such positive charge, you can't get those to come together and make an oxide mineral. There's such positive charge there that you're instead going to repel this if you get them close together. The only way you make a mineral is to go down here and get something like potassium or some such thing and have instead a very low charge ion in between to make, say, a potassium nitrate or a sodium nitrate, a calcium carbonate, even in a sense, that, yeah, you've got great charge, low coordination number, but you just can't make then an oxide, and instead are going to have to make, like I say, nitrates, carbonates, sulfates, etc. there. If we go to the middle, on the other hand, we hit kind of the nice compromise of this business. So we're over to thinking about, again, these being oxygens, probably most readily these being aluminums. There can be lots of these things here, aluminum, titanium, etc. Where we're now looking at cations, fairly highly charged, but certainly not like a +5 or +6. So like I say, aluminum +3, titanium +4. We're now looking at a larger ion, and so can get, say, 6 or 8 oxygens around rather than just 3, and so can begin to shield one of these positive charges from the other positive charge, don't get the repulsions that would have torn apart an analogous mineral over here, and instead get something so you don't get those repulsions. You can actually make oxide minerals like corundum, which is going to, at least conceptually, be a big player here. But it means also this is where then you get the cations that can go into early forming igneous minerals. Still a high energy situation, but they can begin to come together to make then things, again, like your magnesium silicates up there, your calcium and aluminum silicates, your inorthite, and so on. You can get oxide minerals and high temperature silicate minerals to form from those things. Swing on over here, and you're to the now big things of low charge like potassium or more so rubidium, barium, etc. Not much charge, lots of oxygens around them because they're so big that now coordination number is much larger. So you get a little bit of charge distributed across a big area. You can't make an oxide mineral here because the thing will just fall apart. Over here, the problem was you would have repulsions between the intense positive charges. Here, the positive charges are so weak that it's really not going to hold itself together very well. And instead, thinking about the igneous processes, this is where you have to wait then for potassium to finally start entering the later minerals of Bowen's reaction series. And so end up not with red symbols for early forming igneous things, but instead late ones. So, it's a horrendous diagram. I think it's so important in explaining what goes on that it's actually in a very, very simplified version down there to try to explain what you see then here. But you have an explanation then of why those three tracks exist. And one of the neat things about it, it does become then useful to thinking about high temperature geochemistry, igneous petrology in terms of, making, say that early anorthite, but also low temperature chemistry. What's going on in soil formation, useful to aqueous geochemistry, even if you don't care what a mineral is. And just are thinking about river water, seawater, it's beginning to tell you why the things you're seeing in those waters are what they are. And again, because the nutrients have to be soluble, the symbols for nutrients are telling you something about biochemistry that you wouldn't expect to, I think, work out so well on a periodic table. Can even take the aqueous geochemistry thought a little bit farther. And again, I make then another table like this thing. But to talk about aqueous geochemistry, work across the same arrangement of sodium, magnesium, aluminum, silicon, phosphorus, sulfur in that row. Here, things that in solution just hydrate. Potassium, for example, will attract water molecules, but its charge is so small and it's so big, it's not going to reject off any of those hydrogen ions. It is just something with water molecules stuck on it. Go over to in this row where I really should have been, to aluminum. Now enough concentration of positive charge that it rejects some of the hydrogen ions off the water molecules. So you start getting ionic things in solution, the hydroxo complexes, it says here. Move on across to silicon, and you're now off some of these, could think of them as were water molecules, both hydrogen ions, so you do oxo-hydroxo complexes. And finally out here, where we kind of started talking, phosphate, sulfate, nitrate, to purely oxo complexes in solution. So like I say, you don't even have to be interested in minerals to be getting something out of this arrangement of the periodic table. So you get some patterns of behavior of matter and nature that are being expressed by those strings of color that you're seeing in the Earth Scientist periodic table. If you're, say, taking mineralogy, I certainly encouraged mineralogy students to come here today. You begin to be able to say things then about the properties of minerals and begin to predict the properties of minerals. For example, if you want to look at melting temperatures, and again, to keep life simple, this is melting temperatures of oxides. Your highest melting temperatures are in that middle ground through there. Over here, weak bonds that won't let those oxides survive at high temperatures. Over here, too much repulsion to let them survive at any temperatures. But you can begin to predict melting temperatures and make sense of them with this table. Solubility. So if you can see up here, we're looking at solubility constants. Again, a fairway here of the least soluble things because they're holding together best because they're balancing charges. You're too much positive charge, you're not enough to hold things together. Hardness. I don't know what, again, the undergrads are taught here in terms of determining hardness of minerals. I think one first thought might be, well, bond strength, how much something holds together, should determine how hard a mineral is. But if you start calculating bond strengths, you go to quartz. Easy enough to do, silicon dioxide. The silicon has a +4 charge and it's +4 coordination, so it's got a bond strength of 1. Corundum, well, it's aluminum, so it's only got a +3 charge. It's aluminum in 6-fold coordination, so the bond strength's only a half. So by the logic of bond strength, quartz is the far harder mineral. And so, no, you find that, yeah, here is again that fairway of hardest minerals that's representing or resulting from, I'm arguing, that compromise of repulsion and attraction. And on the other hand, your quartz with that wonderful big bond strength, you can scratch if you so choose. Last in that list, kind of the same thought of doing bad things to minerals. Hardness is about scratching the surface. Bulk modulus is about how much a mineral can be squeezed, in a sense. The greater the number, it's greater its compressibility. And again, the things, the less its compressibility, the things with the biggest numbers here, the most resistant to compression, are in that fairway. And so again, are showing you a pattern that I think gets back to that strength of some attraction, but not so much positive charge to be repulsion. Thoughts? Last property is the easy one, color. And at this point, I'm going to have to not just talk about the hard cations that have lost all their outer shell electrons, but get us over here to where we said, no, these things do have some surviving outer shell electrons, even though they are positively charged. So again, iron +3, nickel +3 and 2, copper down to charged silver and gold, if you like. But get over there, because it's over here, do you get all these beautiful minerals? And what you're seeing is, as you probably know, most color in minerals has to do with light interacting with outer shell electrons. And so we've got to be into what I'm calling the intermediate cations here that do have some outer shell electrons to get all this wonderful color. On the other hand, go back to the left to our hard cations, and one of the ones that have lost all their outer shell electrons, dull and boring. Either white, clear minerals, or at most kind of a brownish, you'll see here in a second. I don't know how mineralogy is taught here now, but when George McCormick was teaching us, we in mineralogy in a 15 or 16 week semester went through, had quizzes about different mineral groups as we learned them. And then at the end, we'd learned about all the minerals, so the quizzes were kind of becoming reviews. We had the dreaded black quiz. All black minerals. And the next week, the even more dreaded white quiz. And I look back now and say, that was so easy, because I should have known that if we were doing the black quiz, then all those hard cations out there with no outer shell electrons, forget about them. Because it's got to include then things that will give a dark color, or vice versa, and maybe even more so. The white quiz was easy. You had to be talking about a mineral only of outer shell, or only of hard cations. You couldn't have outer shell electrons, or they'd have color. Little did I know, but there it is. Same sort of thought, more specifically, not even more specifically, about the olivine group minerals. Purely magnesium silicate forsterite. White too, again, just kind of not much color at all. And so telling you, yeah, that's something that consists of a hard cation, magnesium silicate. And on the other hand, go through the olivine spectrum to phaelite, and you're to a black mineral, neither of which is what most of us think olivine is, because the old, if it's green, it's olivine. Well, if it's green and it is in olivine, that means that yes, it's in the middle of that spectrum, has enough iron to give it some color, but at the pure iron end, it gets to black. And again, on the thought of, okay, what's this telling about who's in here? Beautiful purple, I guess, mineral, a magnesium silicate. Again, telling you this has to be something from over there in the middle of the table. It's not a hard cation. So again, making sense of color in ways that I sure wish I'd known when I took mineralogy. This hard cations over here, intermediate cations with some outer shell electrons over here, and these colors then are supposed to represent then the colors of some of those minerals, but works very nicely in predicting mineral color. Okay, we can also begin to predict just the existence of minerals. What minerals seem to work in nature enough to survive, and what maybe potential minerals don't. And in the midst of all these other symbols, there are little diamonds that are simply saying there is, in the case of the blue, a simple fluoride mineral of that cation. So for most of us, we think, okay, fluorite. So gotta have, yeah, right there, a little blue diamond for a fluoride mineral there. The reds are for oxide minerals. And so again, let's go to corundum and go to aluminum and find the similar symbol for corundum. Again, blues are coming out on each side, or well, these blues just over there. And then reds, the oxide makers down that middle fairway. Come over then to where you're looking at the cations that have some outer shell electrons, the intermediate ones, and blow that up then a little more. You'll be glad to hear it. May not help too much in the back, but lots of red oxide symbols there. But progressively you get to bigger cations, fuzzier outer shells. Aren't going to make oxides certainly of gold and silver. That's why we like them, is they won't oxidize. And on the other hand, get down then to yellows, and I'm getting ahead of myself here. We can make sulfides of all these things and get down then to the middle of that. Say those are all making sulfides. These making bromides and iodides, going even farther down the right side of the table, but can begin to say, yeah, those are the sulfides. And to be clear, sulfides of minerals are one cation. This is simple mineralogy. We aren't going to come up with three things to write in a chemical formula. But those are where all our sulfides, and like I say, then bromides and iodides fall on the table. And if you're saying, that's all, what about that left side of the table? No, there are no sulfide minerals made from, say, a calcium sulfide, a magnesium sulfide. Nope, doesn't exist in nature. And again, I think, I wish I'd known that when I took mineralogy. Could have when we knew we were looking at a sulfide mineral, say, don't even think, if I'm having to figure out what that mineral formula is, don't even think about that stuff. Pattern works. What I just showed you, this is a figure from a paper that was published kind of as an outgrowth of the periodic table, showing you the same thing though, that the reds, big red balls are carbides actually. Oxides get these smaller reds, but thinking about these things that combine with the harder cations, as you go down to bigger, fluffier anions, down to bromide, down to iodide, down to bismuthide, you're seeing instead that yes, those bigger, fuzzier anions then bond to bigger, fuzzier cations and give you then, like I say, iodides, bismuthides, if you care about them down there. But my point would be simply there is a pattern to all these chemical formulas of minerals once you have a table that lets you see that working out that way. Thoughts? So yeah, we can predict the existence of minerals. There are 2 or 3 more figures that I'm going to save you from that would get us into more detail than we want. Go on to say then, yeah, what's this doing for us? In a lot of different ways, and I think maybe I've already made my case about conventional geology. You're beginning to see that you have patterns that can give you predictability. It's also useful in the environmental side of the earth sciences. And to take just one example here, let's go back to chromium and chromium plus 6 there because it's lost all its outer shell electrons and so is over there in the hard cations. And on the other hand, chromium plus 3 and plus 2 still have some outer shell electrons. So they're over here in the intermediate side. But you also then are seeing, and yeah, they've got all these red and whatever symbols over here. The chromium plus 6 doesn't have much symbols at all, except to say that it will make an oxisalt mineral, excuse me. But my point would be that has an environmental implication. that all these things over here are soluble in water, these over here much less so. And if you start then reading the literature about chromium in drinking water, what you find is that chromium's certainly not very good for us in our drinking water, especially that form, because it is soluble. It's going to go through your cell walls. It's going to get into you, not just that you're going to drink it in your tap water, but it's going to go through your cell walls and interact within your cells. These things, on the other hand, are so much less soluble. They aren't going to get to you. And so, again, I'm apologizing that this is showing up so small to you here, but it's telling you that, yeah, chromium plus 6 appears to be absorbed from the gastrointestinal tract to a greater extent than chromium 3, and we don't even bother with chromium 2. But you do then begin to see the things that are hazardous to you, or you're thinking about as being hazards environmentally in groundwater, are having to do with oxidation state that, again, begins to be something you can see on a table like this. And certainly you wouldn't get out of a conventional table that chromium was just elemental chromium. I'm sorry, I could have blown it up a little bit more. It's all the same. Chromium plus 6 appears to be absorbed from the gastrointestinal tract. Sorry. So like I say, one example, but I think you could probably similarly start talking about vanadium over here being more soluble. Again, in fact, it is soluble enough that we actually, in some cases, see it as a nutrient element. Over here, less soluble, so on there. So that's the environmental side. Thus far, I've been trying to present patterns to you. My last thought, you might be glad to hear in this yellow list, is instead to say, well, you can also look at this in terms of kind of special cases and why they are the kind of strange things they are. And you're probably thinking I'm going to drag you off to some weird thing you've never heard of before. But in fact, my special case here that I'll use as an example is silicon. The thing we think of as very, very familiar to us. And think about silicon plus 4. Go to silicate melts. It is, we call them silicate melts, the most abundant cation in silicate melts. Bonds the most strongly with oxygen if we go back and think about calculating bond strengths. And so if you knew nothing else, and everybody in this room knows the opposite, but if you knew nothing else, you'd say, wow, this is a tremendously abundant thing in magmas. It bonds really strongly. It must form the first mineral to form as a magma cools. And yet you'll know it's exactly the opposite. And so you look at this and are left thinking, well, why is that? Why is silicon instead last going to get you down to where you make quartz, to the cooling of a magma? If you look at this table, I think the answer emerges. That you have here with all these red symbols, those things that go into mostly, I was marking oxide minerals, but certainly the things that go in from magmas into solid igneous rocks early on. Over here, the blues, my blue lines, to the solids that won't even make an oxide mineral, certainly aren't going to get you into making an igneous rock. And silicon's right there on the borderline. But once you put silicon in that context, you realize it's in a really strange situation. We think of it as so fundamental to our silicate minerals, but over here, you've got things that won't even make an oxide mineral. And so no wonder that silicon dioxide is kind of slow to finally form, because it's on the transition to things that won't do that at all. And so helps you begin to contextualize silicon a little bit. That's the igneous petrology side of things. Go to hydrology and aqueous geochemistry. Groundwaters are commonly supersaturated with respect to quartz. This is a plot of concentration of silica in solution in groundwaters versus depth. We're down to 1,000 feet, 2,000 feet, and eventually down to 5,000 feet. Each symbol is a groundwater sample with a chemical analysis that I could then stick a symbol on here for quartz or silica dioxide concentrations. The vast majority of them, you're seeing supersaturation with respect to quartz, and we're talking double, triple, quadruple supersaturation. Again, you think, well, quartz is a really common mineral, but what you're seeing is that failure to nucleate because, again, getting those silicon plus 4s together to make quartz, in this case precipitated out of groundwater, is a somewhat unlikely thing. That's from the groundwater side. The sandstone petrologist could tell you the same thing. Picture here of a quartz-rich sandstone, quartz grain, if you can see the outline of the original rounded sand grain. Similarly there, the original outline, some quartz overgrowths on those quartz grains. Yes, groundwater precipitated silicon that gave you these nice crystal shapes there, that you could get silicon to precipitate on a pre-existing nucleus. You couldn't get it to precipitate anywhere else. There's nowhere in this rock, and this is generally true of sandstones, that you don't see newly nucleated quartz crystals as cements. Instead, you see them as overgrowths on some handy pre-existing substrate. Instead, for example, calcium carbonate, that's what's showing up as yellow and whatever that is, it's willing to nucleate de novo, if you like, in the pores of that sandstone. But silicon's position there means, no, I'm not gonna nucleate, because there is that positive concentration of positive charge that is going to make that hard to do. Last, we've already been here talking about quartz bond strength. And that's, as I noted, greater than in corundum, but it's not the hardest oxide. And so again, we're having to come back and say, why is it that silicon dioxide, our favorite, our most abundant mineral seemingly, just won't form readily? And I think it's about that boundary position, which gets me through all those thoughts. I spent all my time over here because I really think this is where the interesting stuff is. So to briefly go to the other side of the periodic table, over here, fluoride, chloride, bromide, iodide, the minus now 1 anions, the -2 anions, -3, -4, which is pretty lonely, because really, unless you're thinking about methane, you're pretty much out of luck thinking about carbide minerals much, and certainly about silicide minerals. But over here, kind of the mirror image of what you saw, that you're making a transition from things soluble to, as you go inward, to greater charge, things that aren't as soluble, and so start making more minerals. But there's really not a whole lot more to say. And in fact, if you're thinking, well, why doesn't this go as far? You can only get to that -4 charge and you're done. Over here, you're going to +5s, +6s, and so getting into a different territory to make kind of the threefold division there. You can't get to it over here. Since basically what you're seeing from an atomic sense is you just can't keep adding on electrons. You can't have a -5, a -6 kind of charge on anything. So I think there's really less hay to be made there, and so that's why I haven't talked about it. It ties in then to where we were before, that this, in terms of thinking about what minerals, or what anions go with what cations to make minerals, you're seeing the same thing as that. And last, and I leave it last because I really have little to say, is the periodic table of the elements. Period, the elements. This is showing you these things that exist in nature in elemental form. And the left-hand side of it, if you can't read it, is chromium, tantalum, ruthenium, if you know ruthenium. But my point is, again, all our sodium, calcium, magnesium, etc. over here don't make a native element mineral, and so they're not evident. And really, the periodic table of the elements for scientists is only that, and doesn't to me tell you much either. Now, that's partly because I'm not an economic geologist. Perhaps some of you in the room could start saying interesting things about what goes on within there, but I'm hard pressed really to see very much. And so it's why I stuck it to last, and left it then to say, yeah, we have now made our way across the entire thing. If you're interested in this, I know you folks, I'm very pleased to see, have a printout of the table in the hallway. But if you want your own copy, just go to my website, railsback.org. There's a whole page this leads you to. You can in fact get the Earth Scientist periodic table of the elements and their ions in German, in Spanish, in Portuguese, in Catalan. Then that's just people emailing me and say, "Can you send me a blank copy?" And I'll translate. Miraculous. Oh, it's in Chinese too. So anyway, it's there. You're welcome. Absolutely, download it. And the PowerPoint file of this talk will be there for you as well. And so that is there for you. And with that, I can say thank you very much.
I was getting my economics degree when you were finishing up your master's, but you mentioned scandium. Well, scandium does occur in carbonatites, as do, if you look at your periodic table, rare earths, thorium, scandium, and yttrium. In fact, I spent a fair amount of time doing carbonatite exploration, which is the rock in which those elements occur. And in Nebraska, the Elk Creek carbonatite, which is currently being touted, one of the things they tout is it does contain scandium. Now, I worked for Unicom and Molecule, we discovered that, and at that time, scandium was known, and still to this day, but now it's being touted as a critical mineral, critical element. But there's so little of it produced, you probably did struggle with trying to find out, anything about it. But it's supposedly used as an alloy with aluminum and aircraft and defense things. But it's interesting that your column there with rare earths, yttrium, scandium, all those elements are found in carbonatite. And as you know, they have a mantle component, but they are a low temperature. If you look at today's modern analog in the East African root, there's carbonatite magnet. I think it melts at like 600 degrees. So it's a low temperature magnet. But not that one's mineralized, but the mineralized carbonatites all follow, the elements that you have listed there are all things that we find. And speaking of environmental, thorium is an environmental concern with a lot of carbonatites and anything to do with extraction of earth, you have to deal with thorium usually. Whether it be in monazite, which is the placer rare earths and critical elements, or as in Mount Bastosite, which is a carbonate, fluorocarbonate that contains all those rare earths. And I'm not sure how that fits in with fluorine and the carbonate, and then for monazite, it's a phosphate-bearing rare earth element. But anyway, that jumped out at me, especially when you mentioned scandium. I couldn't wait to say, hey, scandium, Elk Creek carbonatite in Nebraska.
Okay. Thank you. You probably told me much more about scandium than I ever knew before. Thank you. Thank you. Yes.
This is awesome. The thing that I was thinking about is, what is the relationship between these fairways that you're talking about as well as with the redox ladder? I hadn't even thought about it until seeing the talk.
Okay.
I see a little, Brad, I see a little bit of it with the vanadium and the molybdenum pattern, like following the orange. I can start to see some of the redox ladder starting to show up a little bit in there. I hadn't thought much either, but seeing that, it starts to partially come through, especially in oceanic conditions with low oxygen.
Okay, so did you be heading then to the left from? Yeah. Okay. Yeah, I think I hadn't thought of it in those terms, but you're absolutely right. Yes. And
yeah, because my lab down at Florida State, when I was working in masters, we worked with thallium, vanadium, and molybdenum.
Okay.
To track those in redox and low oxygen conditions.
Okay. Yes.
Is there a reason that the contour lines are curved? Like, can these hard cation ions have multiple ionic potentials, or is it just for artistic?
No, I'd say they're curved because the easy one is calcium. Comes to a 2.0, so the line's going to go through there. Here you start calculating ionic potential, and sodium's pretty easy too. It's just a little bit more than 1. On the other hand, magnesium, charge of 2, radius of about 0.65, so ionic potential of 3. So the 2 just has to kind of go through the middle of this box, because for calcium it's 2. Here I've got 1, here I've got 3, so I've got to curve it to get between those. So I'd say I'm contouring it just like I'd contour a topographic map that I've just, when I made it, I just had for each of these and ionic potential. In fact, I think I have a slide that I'm not going to try to get us back to, where yes, I just calculated the ionic potential of each and then contoured. So no, I wouldn't say that's, I don't see how it could be anything other than what it is contours.
Okay, thank you.
Yes.
So some of these questions that are being asked really kind of accentuate the big question that I've had during your entire talk, and that is, obviously you didn't do this over the course of a week. And you had some starting questions, but what I'm really curious about is, well, obviously as you begin to answer questions, more questions here. So at what point, can you give us kind of a timeline on when you were thinking about this originally, and at what point do you say, I'm tired of thinking of all the connections that are here, and yes, they are there, but maybe you don't ever get to that point. Maybe you're always like, holy crap, there's another connection here.
It was a process that went on a long time. I think, for those of you who aren't aware, this was published in 2003, so you're getting old news here. I think it was in 1999. I was standing in front of a much smaller room than this, teaching a graduate level geochemistry class, and I can't tell you with certainty whether I was talking about chromium or vanadium or whatever, but standing in front of a conventional periodic table and in trying to explain behavior of, like I say, whichever one of those it was, ended up standing there at the front of the room with my arms like that. And that was the moment. I mean, that was that was it. Now, the funny thing was that after class that day, I go back and then start with the very first thoughts of, okay, we're going to make a table that deals with this, so I'm never doing this again. I then realized probably years later that in my lecture notes for that class was in fact a little hint of the beginnings of that table, the beginnings of this table. I think I can get us, yeah, that separation of things by charge of the same element but into different groups. I'd actually drawn 3 or 4 years before that. But yeah, I started in 1999 with that, walking out of that classroom saying something's got to be done here. I think I probably spent 3 years at least then fiddling with it. And that's not a constant 3 years, doing other things, but 3 years of dredging up whatever sets of data I could, and then being to where I thought I could try to publish it. To be clear, that was a battle. I sent it to Science, who sent me back a letter. I'm sure it was just their standard reply letter saying, this is very nice, thank you, but it's just not of sufficiently general interest. And I wanted to write them back and say, wrong rejection letter. No, it's of too general interest. That's why you don't like it, is it's too general. But anyway, I didn't. I sent it to GSA Bulletin, where it got reviewed by 2 igneous petrologists who said, well, it talks about things other than igneous petrology, so who cares, reject it. That was pretty much it. and then sent it to geology, where, again, as usual, 2 reviewers. One, I suspect, an igneous petrologist, because again, pretty much the review was, well, it's got all this stuff that's not igneous petrology, who cares? And another reviewer who said, yeah, this is a neat idea, publish it. And geology is a journal where generally one reject and you're gone, regardless what the other reviewer said. But the associate editor said, no, I like it. And so recommended publication. They published it. And to me, the amusing part was they then said, geology, this is a GSA journal, geology said, well, yeah, we'll publish it, but this insert table is going to cost money. You need to come up with $2,000, and that's $2,000 in those days, to support printing of the physical table itself. Well, it turned out that was easy. I called somebody, the program director for education at NSF, and they said, send us a letter, we'll send you the money. And it was that simple. What I didn't know was that poor GSA, we can't publish this unless you get us this money. Unbeknownst to me, and you kind of question the ethics of this, printed 700 copies and sold them like that. So that was the process. And it wasn't long after publication that GSA came back and said, can we make it part of our map and chart series? And in fact, once they finally sold all those out, so after about 10 years, came back and said, can we print another edition of it for the map and chart series? And I think it pretty much held on until GSA finally said, we're done with maps and charts. Paper age is over. And so that was the end of it. But that's where it went. Oh, yes.
Oh, can you speak to the group with fluorine, chloride, bromine, and formation of evaporites, basically?
In a sense, I think the question is about bromides, fluorides, combining bromine and fluorine, things way over there on the right-hand side of the periodic table that got very short shrift in this talk. And just view them as things of very low ionic potential, so going to be weak to bond. And so, yes, only in the processes of seawater, really only going to go into a solid very, very late, and progressively then as, I can't get us, I don't think, to, well, actually I can get us over to here. As you go down here, see them bonding. Obviously, fluorine with calcium to make fluoride in there. You do have a mineral. You don't have to wait till evaporation processes. But you get down to chloride, which you think of mostly as sodium chloride, and definitely are thinking evaporation. Down to bromides that are even harder to get to precipitate out because, again, you're to now an even bigger ion of the same charge, and so a weak bonder. But yeah, you're looking at these things, not surprisingly, then being there's a seawater symbol, there's a seawater symbol, there's a seawater symbol, there's a seawater symbol. They're kind of the rejects of precipitation of minerals until you get to really highly concentrated brines.
Well, thank you again.
You're very welcome.